Hi, my name is Scott Whedon, and this is my CS5363 vLLM Tensor Parallelism simulation. Through simulation, I managed to double the throughput of a large language model on a production supercluster. Well, it's not, the hardware test hasn't been finalized yet, but it's scheduled and should have for the final report. But the results on this slide preview the key outcomes. Performance gains between 2.2 and 15.5% across tested configurations, an 87% reduction in translation Lookaside Buffer misses by switching from a 4 kilobyte to 2 megabyte pages, and an 18.6-fold speed up in interconnect latency. The core principle guiding this work is quantitative design. I want to make sure that we're measuring and not guessing on a hardware setup for something that is take so long to schedule resources and can sometimes be days before a job will run. We want to make sure that we have the hardware set up and the optimal configuration ahead of time. So before scheduling the jobs on the high performance computing cluster, we wanted to make a hypothesis, run a simulation, and then perform validation. So two independent simulators form the toolchain, each operating at a different level of abstraction. Let me walk through what each one does and why both are necessary. SimPy, spelled SIMPY, is the abstract discrete event model. It is a Python library that simulates system behavior by scheduling and processing events in time order. It does not model every CPU cycle, which makes it fast and suitable for sweeping through many parameter combinations. So you'll see over here on the left side. So the textbook concept starting point was my entire analysis talking about the memory wall. And it actually, when we're deploying vLLM on real hardware, uses a technique called page detention to manage the key value cache. And that stores intermediate attention results during inference. Page detention fragments the cache into 16 block pages scattered across GPU memory. And this fragmentation is efficient for memory allocation, but it creates a hidden problem at the hardware level. So the problem in plain terms is the GPU's translation Lookaside Buffer is the hardware structure that translates virtual addresses to physical addresses. And on this architecture, the TLB has 64 entries, each covering a 4 kilobyte page. And that gives a total coverage of only 256 kilobytes, a tiny fraction of a working set. So think of it like trying to complete a massive jigsaw puzzle, but your desk only lets you look at 64 tiny pieces at a time. You would spend all your time swapping pieces out and never actually making progress on the puzzle. And that's exactly what happens with. So on this slide we have see, the Translation Lookaside Buffer model is a discrete event simulation of GPU TLB behavior under the page attention workload. It does not simulate every CPU cycle in SimPy. Instead, it models the probability that a given memory access hits or misses in the TLB, and based on the page size, working set, and TLB configuration. The simulation parameters shown on the right side of this slide are 64 TLB entries, 8-way set associativity, and 100,000 memory accesses, a 4 kilobyte page size of 4,096 bytes, and a 2 megabyte page size of 2,097,152 bytes, and a working set ranging from 1 megabyte to 256 megabytes. The bar chart tells the story with 4 kilobyte pages, the TLB miss. So moving on to the Gem 5 TLB simulation. Gem 5 independently validates the SimPy findings using microarchitectural simulation at cycle level detail on a x86 MESI 2-level board. The terminal output visible on this slide shows the Gem 5 simulation running inside a Docker container. The workload is page detention micro executing on the x86 64 timing model with 100 memory accesses and a 256 megabyte working set. I tested 3 workloads, each performing memory accesses with 4 kilobyte pages, page detention, random KV cache access over 100,000 entries, a sequential linear scan pattern, which benefits from spatial locality, and random uniform access, which was the worst case pattern. The data TLB miss rates from the terminal output are page detention, 24.1%, with 131,000 misses out of 133 total write accesses. Sequential was 20.8% better due to spatial locality, and random was a 31.4%, which is the worst case pattern. And you might wonder why these numbers are lower than SimPy's 99%, and the reason that I concluded is, so essentially the numbers tell a pretty similar story, 87% versus 99%. The simulators act differently because they're modeling at different abstraction levels, but the direction is unanimous. There's a 2 megabyte super pages dramatically reduced, the translation lookaside buffer capacity misses, and this is not an artifact of one simulation approach, and so it gives a greater indication that we're headed in the right direction on our hardware setup, which we'll come to later on in the presentation. So there's another bottleneck which comes into play, and so far I've shown the page size affects that the TLB behavior, but throughput also depends on how we distribute work across GPUs, and that's where tensor parallelism comes in. SimT stands for single instruction multiple threads. It is the execution model used by NVIDIA GPUs where many threads execute the same instruction on different data simultaneously. The NVIDIA V100 GPU specifications shown on this slide are 5,120 CUDA or CUDA cores organized into 80 streaming multiprocessors, 16 gigabytes of high bandwidth memory, and 2 HBM2 with 900 gigabytes per second of memory bandwidth, NVLink version 2 providing 300 gigabytes per second per GPU, and tensor cores for mixed precision matrix operations. So large language models require multi-GPU setups using tensor parallelism, which partitions matrix multiplication across multiple devices. Each GPU holds a shard of each layer's weights, and the forward and backward passes require AllReduce operations to synchronize. So in this slide, a way to demonstrate visually the major difference between PCI Express and NVLink is the interconnect between the GPUs. And when you have a GPUs set up in a ring where there's a direct connect between each GPU, you avoid the setup of a PCI Express bus where all of the traffic is limited to a single bus. The formula on the screen is Amdahl's law. Rather than reading aloud, let me explain what it actually means for a system. It tells us no matter how many GPUs we throw at the problem, our system is only as fast as its slowest non-parallel bottleneck. And in our case, that serial bottleneck is the AllReduce communication phase where GPUs are forced to wait in line to synchronize their data. AllReduce serialization is the hidden cost of the multi-GPU inference. Tensor parallelism requires gradient synchronization via AllReduce operations, and the GPUs form a ring, each sending gradients to the next. So this creates a serial communication chain that limits speed up. The serial fraction equals the coherence overhead plus the transfer time. NVLink, on the other hand, it provides a dedicated point-to-point express lanes directly between the GPUs, eliminating the traffic jam. And the directory tracks which GPU holds each cache line, so coherence transactions are routed only to. So here are the results of the SimPy interconnect model, or the interconnect bottleneck demonstration. The model architecture shown on this slide defines the inputs as interconnect bandwidth, message size, number of GPUs, and coherence overhead. The AllReduce time equals the number of GPUs multiplied by the sum of message size divided by bandwidth plus coherence overhead. The simulation parameters on the right side are PCI Express generation 3 by 16 at 16 gigabytes per second, NVLink version 2 at 300 gigabytes per second bidirectional, gradient size of 14 gigabytes in FP16 format, coherence overhead of 30% for PCI Express, and coherence overhead of 5% for NVLink. The bar chart shows average interconnect latency by tensor parallelism size. What jumps out immediately is the massive gap between the two bars. PCI Express latency is approximately 480 milliseconds per AllReduce operation, and the NVLink latency is only 25 milliseconds per AllReduce operation, which is an 18.6-fold difference. The PCI Express's high latency, the communication overhead dominates execution beyond 2 GPUs, limiting efficient tensor parallelism to TP equals 2. NVLink's lower latency shrinks the serial fraction sufficiently to enable efficient scaling for 4 GPUs. So Snoop overhead is not related to Snoop Dogg, but it's a Snoop overhead is an x86 modified exclusive shared invalid x86 environment, which refers to the performance costs incurred when processor cores broadcast or monitor memory transactions across the system interconnect to ensure cache consistency. It represents a hidden tax on memory bandwidth, latency, and power caused by keeping data synchronized. So it's slightly different than NVLink versus PCI Express setup. So I have on here the full workload setup, but comparing apples to apples, I'm not sure I would consider the Gem 5 coherence reference similar to the PCI Express and NVLink setup. But we do have similar results where 5% of AllReduce overhead for Snoop traffic and 30% overhead for AllReduce Snoop traffic and PCI. So now we come to the final phase, which will be the hardware deployment. For the super page fix, both simulators show dramatic reductions: 87% from SimPy, 98% from Gem 5, and the magnitude differs, but the direction is unanimous. For the interconnect, both agree NVLink is I would say dramatically faster, but faster than PCI Express, and TP equals 2 over NVLink is the optimal configuration. So that's that's the 4 configurations I want to test on the HPCC, and they're currently scheduled to run within the next 24 hours. There is a resource constraints on the high performance computing cluster, so we do have to schedule and wait, but that is partly the reason why it is important to model these simulations ahead of time rather than trying to guess, because we don't want to sit here and wait every 24 hours when we do a new configuration and to see if that's which one is optimal. So we have in about the next 24 hours, and I believe before the report is due, we will have the final results from the high performance computing centers V100 multiple GPU vLLM. Going beyond that, going beyond one node, we go into the realm of WSC over subscription, which I don't intend to test on the high performance computing center. But as we go into a TP equals 4, that crosses node boundaries, and we could even go into a 4 GPU simulation, or I guess not simulation, but hardware configuration. However, I won't have time to go into that much of a complex setup for this experiment, and I think that a single node 2 GPU parallelism for the so this slide actually needs updating. The model that I ended up going with was a DeepSeek Coder version 2, and that'll be that model can be broken up over two GPUs. So sorry, this slide is not updated, but I have the updated Slurm job will be the DeepSeek R1 just still queue in 14 billion, which is a non-gated 14 billion parameter model running on FP16 format with 1024 token context windows and 100 token outputs. The experiment configuration box on the left shows the 4 configurations being tested. Each one pairs a page size with a tensor parallelism level. So the first one will be 4 KB TP1, second will be 4 KB TP2, and then we'll go into the 2 megabyte super pages TP1 and the 2 megabyte super pages TP2. So the prior reference run on the right shows the correlation coefficient 87.87 between SimPY predictions and actual V100 hardware measurements. Again, this is expected planned output, not yet what we're seeing. So this is I can't stress enough right now that this is mock data to be able to make sure our outputs on the hardware side are the same as our simulation outputs, and we're comparing apples to apples. So this is again planned, and I will have the final results in the report. And so the final conclusion is the optimal setup through the simulators will be NVLink interconnect. Unfortunately, this is not something that I can change if if it turns out that the PCI Express is the setup on the HPCC, and it is a potential snag on the setup. However, the super pages are something that we can change virtually, and through the 2 independent simulators, we get one consistent story. SimPy's abstract model and GEM5's microarchitectural simulation both point to the same conclusion, and through the translation Lookaside Buffer capacity misses is something we can is a bottleneck we can control. The NVLink versus the PCI Express is something that we won't necessarily be able to control on the hardware configuration side. However, it could change whether we are using the TP equals 2 or TP equals 1 for tensor parallelism. So again, the final hardware conclusion will be tested either today or tomorrow, and will be available in my final report. If you have any questions, please feel free to email me at sweden@ttu.edu, and it's just my first initial S, WEEDEN @ttu.edu. Thanks, and have a good day.